In this lecture, we're going to learn about the Deque container class we have in the standard template library. And this is a class that was designed for forced insertions and removal of data from both ends of the container. So if we have a collection like this and it is a deck, it is easy and really performant to add stuff either from the beginning or from the end. So if you need to do more of these kinds of operations, Deque is going to be a really good choice. The name itself is short for double-ended queue, and what this means is that you can do easy manipulations from both ends of the container. This container supports random access iterators, so we can use the square bracket syntax to access data much more easily. The elements are not stored contiguously in memory, but they are stored and organized in such a way that insertions and removals from both ends satisfy these requirements we have here. So these manipulations happen very fast. This is a requirement, and we don't require to move or copy elements as we add and remove stuff, and this is really cool. Another thing is that our iterators don't invalidate when we add elements. So when we add a new element, the iterator is going to keep pointing to the same thing it was pointing to. This is my understanding of this statement here. So in this lecture, we're going to play with Deque and see some things you can do with that. Again, it is designed for forced insertions and removals from both ends. So if that's what you need, Deque is going to be a really good choice. And here is a simple example of how you can create a deck. It is a templated class, so you can specify the type it stores when you create objects of it, and the compiler is going to create a template instance behind the scenes to support this. We can store in integers, so we can put in data here, and we can create a deck for our custom items. This is going to work. And we can pass these collections to our print collection method, and it is going to work out of the box, because these collections support iterators that we use in our print collection function. And we're going to see how this works in a minute when we hit Visual Studio Code. We have a bunch of element access methods we can use. For example, we can use the array index operator to access data. This is not going to do bound check. And what we mean is that if we try to use this operator to try and access elements out of the range of data that we have in our collection, anything can really happen. In most cases, you are going to get a crash. So if you have a collection like this with, for example, 5 elements in, if you try to access elements between index 0 and 4, you're going to get data because we will have data in this collection here. But for example, if you try and access an element at index 10, that's going to fall out of the range of our collection here, and you might really get anything. This element might belong to another collection or even being used by the operating system, and if you try to access it, you're going to get a crash. You are going to get undefined behavior. That's what I mean here. And the square bracket operator here is really not going to do bound check. You need to know that the index you are trying to use with it is within the valid range of the data you have in your container. But the at method is going to do bound check. If you try and access something out of your valid range, you're going to get an exception thrown, and you might catch that exception and handle it in your program. So the at method is a little bit safer than the array index operator here, but you're going to have to choose what makes sense for your application. It is also possible to use the front and back methods to get the front element and the back element. We can use regular forward iterators with a Deque container, so we can set up a begin iterator and loop around trying to find elements. We can increment to move forward in our Deque container and really print or do whatever we want with our elements, just like we are doing here. It is also possible to use reverse iterators, and this is really what we have seen with std vector. In the previous chapter, we have our begin, which is going to give us the beginning iterator from the back. And we're going to use our end to get the ending iterator going backwards. And we can use this mechanism to print data or do whatever we want with data in our container in reverse order. And you can use this if it is what you need in your C++ application. We have a bunch of methods we can use to modify our Deque class. For example, we can clear out all the elements. This is going to delete all the elements in the collection. So if we print a collection with data, we're going to see the data printed out here. We can clear and see that we have no more data in the collection, but we can put data back using the assignment operator like this, and the data is going to go in our container class. It is possible to insert new data, and the way you do that, you call the insert method, and then you specify the iterator where you want the data to be inserted, and the data is going to be put in front of the data that this iterator is pointing at, and you need to be aware of this. We have another method which is going to add more data in our container, but it is going to use the constructor to build the data in place. So if we use our item class and say numbers in place and specify the iterator where the data is going to go, the data is going to be constructed in place. So we're going to use this literal here, build an item object, and then put that at the location where this iterator is pointing, or to be exact, it's going to be put in front of the location where this iterator is pointing at. This is how the in-place method works. We can erase elements using the erase method, and the way we do that, we specify the iterator we want to erase elements for, and the element is going to go. We can also specify a range, and this is something you can do. You specify the start iterator, you specify the end iterator, and anything within this range is going to be removed from your Deque container. And this is something you might want to do at some occasions in your C++ program. We can also use the in-place back method to add stuff at the back of the Deque. I think we also have an in-place front version of this, which is going to put data in front of the Deque container. We have a pop back method, which is going to remove data from the back of the container. We also have a pop front version, which is going to do the same thing from the front. It is also possible to resize our container, and we can specify how many elements we want inside. This is going to extend it exactly like we did for box container. It is also possible to resize down and really strip down on the size of your container, and any other element that is outside this size is going to be completely erased. And we have a modifier method we can use to swap elements between Deque collections. So we can set up a collection called other items, and we can call the swap method to swap this container with another container. And when you do this, they are going to exchange data. And this is something you might want to do in your C++ program. I try to give you as many examples as I can, but the best source of information is your reference documentation. So if we come to CPP reference here, we're going to see the documentation for Deque. They are going to tell you what it is. And if we go down, we're going to see a bunch of methods that we support. This is the most important thing. We have methods for element access. We have a bunch of operators we can assign using the assign operator. We can use a bunch of iterators. We have forward iterators and reverse iterators. We can use these methods to know the capacity of our container. We can modify it. We can really do all kinds of crazy things. You see that we have a bunch of operators here, but our comparison operators have been removed in C++ in favor of the three-way comparison operator, and you can use it to do all kinds of crazy things. If you go down, you're going to see a simple example of how you can create and use a Deque. For example, we can create it like this and put in data. We can push data from the front and from the back, and we can print data out, and you can really do all kinds of crazy things with this. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Here we are in our working folder. The current project is Deque. We're going to grab our template files and put them in place. Let's do this. And let's open this up in Visual Studio Code by dragging and dropping here. This is going to give us our main CPP file that we can clean up a little bit and remove what we don't need. And we're going to include our Deque header. We are going to set up a simple item class that we're going to use to show you that it is possible to store custom types in these standard container classes. We will also give it an output stream operator, which is going to be used to print this thing on the output stream or on stdcout in our case. It is not going to be a friend function because it's going to be using a public method to get the data that we want to print. This is going to work just fine. And we will set up a simple function which is going to print our collections. It is going to be a template function which is going to print things out using forward iterators. So we're going to go from the beginning, loop around, moving forward in the container and printing each element we find by dereferencing the iterator here. And this is going to work pretty well. We have done this a couple of times by now. The first thing we're going to do is to create Deque containers. We can go down and put in the code to do that. We can say std Deque, specify the type we want to store in, and really put in the data. This is going to do. We can even do this for our custom types. So we can store in items, and this is going to work pretty well. You see that we are building them in place. And if we loop around trying to print each element, we're going to see that our numbers are going to be printed out and our items are going to be printed out. Let's pass this through our compiler. We can use GCC to do that. And the build is good, so we can bring up a terminal window to run our program and see what we get. So let's clear and run Rooster. And we will see that our numbers are exactly what we put in, 1 through 6. And our items are the data that we just put in here. And you see that we are using our output stream operator for the item class here. So we have our item data and everything is as we want. We can store data in our Deque. One thing I want you to appreciate is the similarity of how you use these containers. So for example, if we want to switch which container we want to use, all we have to do is change the name. So for example, we can change this to vector. This is really cool. And this is by design. So if we change this to vector and include vector on top, code is going to work. You see that the compilation is going to go through and our code is going to work exactly the same it did, even if we changed the way we store our data on the inside in a really big way. So let's clear and run Rooster. You're going to see that we're going to get the same thing regardless of the container that we are using. But these containers are really different behind the scenes. And some are going to be good for some things and bad for some other things. Let's turn this back to use std Deque. And we can go down and say Deque here. And we're going to do the same here. And this is going to work as we want. Hopefully this is a good example to show you how you can create Deque containers. Again, the good reference you have is the official documentation. Go here and really learn about all the methods and facilities you have to make your life easy in your career as a C++ developer. We are going to go down and look at a bunch of methods we have to do element access. We can use the array index operator here. This is going to work, but this is not going to do bound check. And what this means is that if you try and access something out of the range of data you have in your container, things may blow up in your face and you need to be aware of that. The at method is going to be a little safer in that it is going to throw an exception if we try and access elements out of our valid range. So if we try and access the element at index 30 here, this is not going to do bound check. So it is going to silently give you undefined behavior, and this is really bad. But if we use the at method, this is going to throw an exception, and we might catch this and handle it in our C++ program because we already know how to work with exceptions in our C++ programs. We also have access to the front and back methods. We can try and run this program to see this. So let's pass this through our GCC compiler. The build is going to be good, so we can clear and run Rooster. And we're going to see that if we do element access at index 3 in our numbers collection, 0, 1, 2, 3, that's going to be the 4 here. If we access the element at 3 using the at operator, or the at method, I should say, we're going to get the same data. If we try and use the index 30, this is going to give us a 0, but this is really undefined behavior. Sometimes you might even get a crash. We can use the front method and the back method, and this is exactly going to give us the data that we have in our container here. Now, I want you to see that if we use the at method and try to go outside our range, we're going to get an exception thrown. And because we're not handling this exception, our program is going to crash. You probably know this already if you have watched the chapter on exceptions in C++. Let's pass this through our compiler and show you that The build is going to be good, but this is going to blow up if we happen to run our application. And you see that we have an out of range exception. And if we handle this in our program, we're going to be able to recover from this problem. And this makes this method a little safer if you have more chances to access data out of your range in your container. So make sure you use this to your advantage if you happen to need this. It is possible to use forward iterators in our container, which is going to be Deque in this method, in this case, I should say. So here we are setting up a begin iterator, which we're going to use to loop around. And then we're going to loop around, incrementing to move forward in our collection. And at each iteration, we're going to print the current element by dereferencing our iterator here. And you're going to see that we're going to be printing our data. This is actually the same thing we are doing in our print collection function, which is really working pretty well because this container supports the iterators that function needs. We can pass this through our compiler to see if the build is good. The build is good, so we can clear and run rooster. And we're going to see that if we use our iterators, we're going to be able to print our data. This is going to work pretty well. We can also use reverse iterators if that's what we need in our C++ program. The Deque container supports all these iterators, and this is really cool. So we can put up our reverse iterator, which is going to be the beginning from the back, and we can loop around until we hit the reverse and iterator, printing each element at each iteration using the dereference operator. And at each iteration, we're going to increment our iterator to move further back in our container, and this is going to do exactly what we want. Our elements are going to be printed out in reverse order. Let's pass this through our compiler. The build is going to be good, so we can clear and run rooster, and we're going to see that if we print in reverse order, we will get 6, 5, 4 all the way to 1. This is really cool. We also have a bunch of methods we can use to query for the size or capacity of our container. We can use the size method, we can use the max size method, we can use a method to check and see if our container is empty, and you can use these if they make sense for your use case. Again, you can come back to the official documentation and know what all these methods mean. I didn't tell you what they do on purpose because I want you to really be able to go in and find things on your own. So here we are pushing back, and we are going to see that the size is going to grow. This is what I want you to see. So let's pass this through our GCC compiler. The build is going to be good, so we can clear and run rooster, and we're going to see that our size is going to be 6. The max size is going to be this number here. So what the hell is happening here? We can go back to our documentation and see what the max size method does. It's going to return the maximum possible number of elements you can put in a Deque. And on our system, this happens to be really huge. So this is the case here. We can check and see if it is empty. In this case, it is not empty. And after we push a new element at the back of our Deque, the size is going to grow by 1. And this is really what I want you to see here. Use these methods if they make sense for your use case. Now that we know all these things, we can also look at a bunch of methods we can use to modify our collection. For example, we can clear all the elements and make it empty. And after we clear, we're going to print the collection and see the size. And we're going to put data back in and see how the size changes in our collection here. We can do things like this. So let's pass this through our compiler. The build is good, so we can clear and run rooster. And we're going to see that before we clear, our data is going to be this. And after we clear, the collection is going to be empty and its size is going to be 0. But after we reassign data, we're going to see that the data comes back and we can print it out and see it. This is going to work really well. Use these things if you need them in your C++ application. Another thing I want you to see is the insert method we can use to put data in our container. The insert method is going to insert in front of the iterator that you pass here. So for example, if we insert 300 here, it is going to go in front of the location where this iterator here is pointing at. So let's try and run this and show you how this works. I think that's going to be much easier to explain. So the build is good. We can clear and run rooster. We're going to see that before we add our element, we have 10, 20, 30, 40, 50, and 60, and but we are going to find the iterator that goes to the second index. So the second iterator is basically going to be pointing at the beginning iterator plus 2. So it is going to be pointing to the 30 here. Let's make sure you can see that. Here is where our iterator is currently pointing. You see that our iterator is pointing to the begin iterator plus 2. So our begin iterator is going to be at this 10 here. And if we add 2, we're going to hit the 30. So this is where we are pointing before we insert our thing here on this line. Now, if we do the insert we are doing on line 143 here, we are going to insert the new piece of data in front of the location where the iterator is currently pointing. So our new piece of data, which is this 300 here, is going to go in front of the 30 we have here, and that's what we see right below. So 300 is in front of 30, and we achieve this with what we have on line 143 in our code. Now, after we insert the 300, the iterator is going to keep pointing to the 30 where it was pointing at. Now it is going to be pointing to this 30 here, and if we insert 400, we're going to see that the 400 is still going to go in front of the 30, and that's what we have right here. And after we insert the 400 here, our iterator is going to keep pointing to our 30. So the iterator will be right here. This is really critical to understand. It is also possible to use the in place method. The in place method is going to build an item in place and put it in front of the iterator where we are pointing. So if we go in our numbers collection again and insert at this location, begin plus 2, we're going to see that the 45 is going to be put in front of the data that we have at this item position iterator here. And that's what we're going to see. Let's try and pass this through our compiler as usual, and we're going to try and understand what is happening. The build is good. We can clear and run Rooster. And we will see that our iterator is going to be pointing to the third item. So we will have a situation like this. So this is going to be where our iterator is going to be pointing. We're going to place a 45 in front of the location where the iterator is pointing. So the 45 is going to go in front of the 300 here, and that's the case. And after we place, our iterator is going to be still pointing to 300. You need to understand this. It is also possible to erase elements from our Deque collection. Here we're going to set up a collection and print it out, and then we're going to erase the element at this iterator. So numbers begin plus 4. We're going to remove the fourth element. We're going to print our collection at line 170, and then we're going to erase from a range, and the range is going to be from the beginning iterator plus 1 all the way to the beginning iterator plus 4, and we're going to see that the elements are going to go away. We can do something like this. Let's pass this through our compiler and see what is happening. The build is good, so we can clear and run Rooster. And at this moment, we will have our data, which is going to be 10, 20, 45, all the way to 60 here. And we're going to erase the element at the beginning iterator plus 4. This is what we do on line 168 here. So let's find this iterator. We're going to visualize it. We can go in our collection. This is the beginning iterator, so plus 4. 1, 2, 3, 4. So we will be pointing to the 400 here, and we will remove it. And after we erase the 400, we're going to end up with something like this. And you see that the 400 is gone. And we can remove a range now. So we can say we want to remove from the beginning iterator plus 1 all the way to the beginning iterator plus 4. So beginning iterator plus 1 is the 20 here. So this is going to be our starting point. And we want to remove elements all the way to the beginning iterator plus 4. So we will do beginning iterator plus 1, 2, 3, 4. So we're going to remove all the way to here. These elements are going to go. And if we look down here, we're going to see that 20, 45, and 300 are gone. So what we remove is a range, but the last element in the range is not included in what we remove. You should really understand this. So 20, 45, and 300 are going to go, and 30, 40, 50, 60 are going to be left in, and that's what we have here. This is how these methods work. To really understand how they work, sometimes you have to put up a simple piece of code to see and understand what is happening behind the scenes. Another thing we can do is add an element to the back of our collection. For example, we can do in place back. This is going to build an element in place and add that to our collection. That's what the in place method does. We're going to print our collection and see what is in, and then we're going to in place a few numbers and we're going to see what is inside after our modification here. We can pass this through our GCC compiler. The build is going to be good, so we can clear and run rooster. And we're going to see that we have this data here, and we're going to in place back 10, 11, and 12. We're going to see that the data was added, and this is really how we can use the in place method. We can also pop back, so let's go down and do that. We will use the pop back method. We will print our collection and then pop back one element by element, and we're going to see that the 12, 11, and 10 are going to go away. And we're going to be left with whatever we had in before we added these little things here. Let's pass this through our compiler. The build is good. As you see here, we can clear and run rooster. We will see that we had the data here, but we're going to keep popping. The first time we do that, 12 is going to go away. The second time we do that, 11 is going to go away. And the third time we do that, 10 is going to go away. And that's going to be the data we are left with. It is also possible to resize our deck, so let's try that out. We can put in the code here, and we're going to say that we want to experiment with resize. We will print our collection and see the number of items inside right here. And then we're going to resize it to 30, and we're going to print it out again and see the size of the collection after we resize it. Let's try to do that. We're going to build this using GCC. The build is good. As you see right here, we can clear and run rooster, and we will see that before we resize, we have these items in, and the number of items is going to be 5. And if we resize our collection, the collection is going to grow to have 30 elements in, and the elements we didn't have in before are going to be 0 initialized. You should understand this. It is even possible to resize down. So after we resize down, we're going to see that we're going to be left with 10 elements, and many elements are going to be thrown away from this collection here. And this is how the resize method works. Keep in mind that it is even possible to resize down because this is not something you see a lot in containers out there. The last thing I am going to show you in this lecture is that we can swap things out using the swap method. We will set up a deck of items and we will print out our items. We're going to print out items and other items, and then we're going to swap these two things. We can either call the methods on items or other items. This doesn't really matter. And we're going to see that the elements in these collections have been swapped. Let's pass this through our compiler to really show you this. We're going to use GCC as always, and the build is good now, so we can clear and run rooster. And we're going to see that before we do the swap, items contains 22, 33, 44, and something here. And other items contains 100, 200, and 300. And after we swap the elements out, we're going to see that items now contains what was in other items. It contains 100, 200, and 300. And other items contains 22, 33, 44. You see that the data has been swapped. And if you really want to understand the behavior of these methods, you can either try them out like we are doing this in our code, or even better, you can check the documentation. You're going to see what these guys do. For example, if we open up our swap method here, we are going to get the information. It is going to exchange the contents of the container with those of the other container. And you're going to have even more information that I could give you in this lecture. Down here, we even have a bunch of examples. So to really use these things, the best place to get information is from the reference documentation you have for the C++ standard library. This is all I had to share in this lecture, showing you how you can use the Deque container. Again, this is very useful if you can do insertions and removals at both ends of the Deque. That's going to be super fast, and this is going to make your code much more performant. We are going to stop here in this lecture. In the next one, we're going to learn about the forward list container. Go ahead and finish up here and meet me there.